Welcome to this third webinar, part of the Flex Industries project. Today we are going to talk about grid-connected decarbonization and flexibility technologies in industrial plants. And I'm here today with Francesco Ghionda from our partner FBK. Just before leaving the floor to him, I wanted to remind you that this meeting is being recorded and it will be available on our project YouTube channel, so you can watch it there again if you'd like to. And remember to stay connected and updated on our social media channels to stay updated on the project, and we will let you know there also when the recording is available. So I think I can leave the floor now to Francesco.
Okay, thank you, Martina. Okay. Okay, I think you can see the presentation. Thank you, Martina, for the invitation. I ask also Niccolò if you want to do a brief introduction, or I can start with the presentation.
Hello, everyone. Good morning. Thank you to all the attendees to be here today for this third Flex Industries meeting. So today we're gonna talk about a very crucial aspect of our Flex Industries project, which is the all of the aspects regarding the introduction and implementation of grid-connected technologies inside the industrial power plants. As you may already know, inside the project we have covered different aspects, from the renewable energy to the waste heat recovery technologies. And today the focus is more on some technologies that are being already implemented in the demo, in one of the demo sites, Small Pharma. So sorry for the spoiler. And mainly focus on the photovoltaic battery, the best, and the heat pump. So again, sorry for another spoiler. So yeah, we are very happy to hold this third webinar. I think this is it for the introduction, and I'll leave the floor to Francesco to jump in the more technical aspects of these implementations. So thank you, Francesco.
Yeah, thank you, Niccolò, for the introduction. And yeah, I'm Francesco Ghionda from Fondazione Bruno Kessler. And as anticipated by Niccolò, I will discuss about the Italian demo site of the 6th demonstration site in the Flex Industries project. And in particular, I will give you some details about the Italian cluster made up of for the demonstration of these innovative actions. In particular, the demo sites from Pharma, and has Fondazione Bruno Kessler as a research and technology center that support the scientific output of toward the project and toward the scientific community, and IREF and MEDAC, that we will see later on in the details, are the technology providers of some of the innovative actions in the project. To give you a brief, let's say, introduction on the aims, the route where all this starts, where all this come from, the needs for decarbonization and flexibility is rooted into, of course, the need for decarbonization of the industrial sector, the effort from the EU Commission and the European Green Deal and Fit for 55 package toward reducing emissions. This, of course, is an important starting point for industries, but also is a also strategic opportunities for industry to implement renewable energy, so sustainable production and sustainable, let's say, own generation of renewable energy to supply their process, but also an opportunity to recover waste heat and improve the overall energy efficiency that helps to reduce, let's say, the primary energy need from, let's say, an overall a wider perspective. Along with these two actions, we will see also in details later on when discussing this project is pivotal to, alongside with these actions, deploy digital twins and, let's say, intelligent digital infrastructure like energy management platforms to support energy experts in let's say, making the everyday best decision, optimized decision to manage their energy system. And for doing that, is important that they are aware, they have knowledge, and let's say they are connected with external factors such as the markets, the possible markets where they can provide or sell the flexibility toward the grid, the existing grid. And this, of course, this overall process will help also reducing the dependence on fossil fuels and enhance competitiveness and resilience in general. Going into the detail of the Sonpharma demo site, the company is a leading company for the production and distribution of active pharmaceutical ingredients. That we can see in this slide some of them. The production process is mainly based on fermentation and all the fermentation of microorganisms and all the downstream processes that are required for extraction of the API itself. So here we can see some of them of the main one, let's say, and with an approximate estimation of the pathogens reached worldwide by these pharmaceutical ingredients. The Sonpharma site is located in Rovereto, close to the Fondazione Bruno Kessler, and we are in the north of Italy. Now, shifting the interest and attention to the energy point of view of the production process, and what is the core activity of Sonpharma, I said before, this fermentation and all the downstream activities to extract the APIs. This process requires continuous energy and is running almost every day. Is running every day of the year, continuous operation, and has very strict quality standards required by GMP regulations. So to run this process, this process is several energy vectors and utilities are needed. Energy vectors such as electricity, steam, and cold water at medium temperature and cold water at low temperature. Of course, some of them are or fossil fuel based with like own generation of electricity or production of steam, and let's say natural gas, fossil fuels based intense, like requiring, I said before, fossil fuels for the generation of some of these utilities, or otherwise electricity to, for example, for the generation of cold water at low temperature, or the process air, compressed air that is delivered to the production. So, as part of the Flex Industries project, Swan Pharma took in place these actions that I would like to split into green transition actions. So the implementation of technologies that move forward, allow to advance into decarbonization, and or actions for the flexibility. So allowing, let's say, the overall system to increase the amount of renewable energy based, thanks to the flexibility available on the demand side. So for this reason, the action, what is intended for green transition actions, and along with these actions for the digital transition. So we will see why is important, why is a pillar that should run in parallel with the green transition action. So we will see the details of the implementation about the PV plant, the battery energy storage system provided by MIDAC batteries, and the high temperature heat pump provided by IREF. So the first one is the PV system that is already installed and in operation since more than 1 year, and already generated renewable electricity. The 500 kilowatt plant. We have the battery. The battery developed by MIDAC, 408 kilowatt hour of storage capacity, and 264 kilowatt peak power capacity. I will give you a brief introduction on what a battery energy storage system, BESS, is always made up of a battery rack that is let's say the fundamental component that is made up of several cells, prismatic or cylindrical, connected together in series and parallel to reach the required and desired DC, direct current characteristics. And then we have the power conversion system that allows the conversion of DC power into AC power to be fed to the grid or drawn by the grid. And another important feature we will see are of course the energy management system of the battery. So software infrastructure that allows the communication with and the integration of the system in the environment where it is delivered, and the battery management system that work to supervise what let's say happens inside the battery rack. That is let's say the fundamental unit. Okay. So starting from the design, simulation and prototyping phase, here we see the picture from the CAD design to the first prototype in the MIDAC facility. Along with this activity, the design phase, a simulation campaign was carried out by Fondazione Bruno Kessler, and modeling the thermoelectrical behavior of the battery, simulating charging and discharging cycles to see what is the expected behavior from the expected behavior on the thermoelectrical domains. And as you can see here on the right, some of the results. One important feature and step into the design was the work done for the safety of the system. So first started with the decision to adopt a lithium iron phosphate technology that is among the safest cathode materials for lithium ion batteries. As said before, the cell that compose the overall energy rack, okay, connected in series in parallel gives you the energy rack, and then a monitoring supervising infrastructure to detect thermal runaway and an apex ventilation system to avoid the potential buildup of explosive vent gases, as was prescribed by firefighting authorities, local authorities. That is an important permitting in this case and safety needs for the system is an important step of the overall implementation, since energy intensive industries is very likely that they have already an existing very high requirement for safety management and this kind of risk management especially in the for the firefighting and fire safety. So it is something that should be taken into account in the overall design process. Okay, and finally the integration. As said before, the software infrastructure that allows the battery the best to communicate with the demo site, with some pharma demo site. In this case, the energy management system of the battery is able to exchange data and information with the Sun Pharma energy management system. And here we can see the user interface developed by MIDAC. Finally, the shelter and the integration, the shelter delivered and installed in the Sun Pharma demo site in the Rovereto facility. Okay, next action is the introduction, as I said before, of sector coupling, flexibility, and the valorization of waste heat. I will give you a brief introduction of what is a heat pump. The heat pump developed by IREF for this project, and what is important to recall from a heat pump is that on the evaporation side, the cold side, the secondary medium, in this case water, is cooled, and on the hot side, the condensation side, the secondary medium, once again water, is heated. So at the expenses of electricity. So given that, the developed solution is capable of delivering useful cooling to Sun Pharma, to the Sun Pharma processes, and useful heating to the local DHM. So as said before, valorizing this waste heat, exporting to a local district heating system. And the term high temperature is describing that the temperature lift, the temperature difference is very high, from 10 degrees to around 90 degrees, that is required for district heating. And so in this case, again, we will go into the design, simulation, and prototyping phases of the heat pump development. Well, once again, we supported IREF in this activity with a simulation campaign of the heat pump, simulating the supply of heat toward the district heating, and seeing how the other energy variables like evaporation power or pressure power change at the variation of the hot and the cold, the hot sink temperatures and cold source temperatures. Yeah, the 1.2 megawatt heating and 0.7 megawatt cooling power high temperature heat pump provided by IREF was integrated and into the Sun Pharma energy system, as we can see here, for providing useful cooling to the processes, but also to export useful heating to the district heating. Here some pictures of the implementation at the demo site. Finally the on-site testing when was delivered to the Sun Pharma demo site. Okay, so recalling all the actions for the green transitions. Once we implemented all the technologies, we have the increased flexibility thanks to these new assets, like the battery for, of course, storage flexibility, providing storage flexibility, but also a flexibility of sector coupling thanks to the heat pump that links the electric sector with the thermal sector, and also is improving the overall system efficiency thanks to the mentioned heat recovery and valorization. But another useful effect is the fact that providing cooling to Sun Pharma helps to the reduction of industrial water consumption. So for the cooling, and thus moving a step forward, decarbonization, but also reducing the overall environmental footprint of the industrial site. And along with this, now we are ready for the monitoring period of the demo site, monitoring the new configuration of the energy system. And what is important now is that along with all these actions, this changing into the energy system is important to in parallel develop and have available a digital infrastructure that allows to better understand and control this energy systems. And in particular here, the deployment and the implementation of the action of the implementation going into this direction for Sun Pharma. So to help manage the internal energy fluxes and enhance the awareness of available energy flexibility. So the capability of changing their demand, their load toward the grid. And Trigenia was the partner chosen by Sun Pharma for this solution. Here we can see the two main actions taken place by Trigenia. That was on one side the upgrade of the monitoring infrastructure, taking into account the new assets of the that are the flex industry solution that we mentioned before, but also all the so an upgrade of all the sensors and the integration of these sensors with the existing infrastructure. And the second main action that we can resume is the data harmonization process. So all the operation, including integration, cleaning, normalization, and sharing of data that allows the visualization and also like a useful utilization of this huge amount of data that are generated by monitoring infrastructure. So also enabling this aggregation, okay, of data. And here on the right in the picture, we can see an example of the energy fluxes and the user interface developed for the Sun Pharma energy management system. And as part of the Flex Industries project and as part of the Flex Industries project and the digital transition actions, there is the integration with the Flex Industries platform. So once we have all the information for the energy system available into the energy management system, now there is the possibility to exchange all this information and with the Flex Industries platform. That in this case implemented some forecast that allows to, as we can see here, the demand forecast and cost forecast allows the formulation and provide data for an optimal utility scheduling solution. So if the demo site is aware of what will be the demand and what will be the cost, what is a prediction of is available, the prediction of or the forecast of this signal is capable of solving an optimization problem that gives the possibility to follow, okay, the optimal cost function point. And this is important in this context because allows the energy intensive industry to be aware and always connected to the market, in the sense that is capable to understand if it's profitable to enter into a kind of flexible market, because knows that their cost function, and if this kind of solution can be profitable or not. So a recap in this sense is that if we move on with this overall infrastructure, we have all the information and the sensors available into the energy management system that is connected with the Flex Industries platform and sharing this kind of information. they can have back all the results for following and enabling market signals. So be able to operate and provide flexibility to the market, as we can see here, with the existing own generation capacity or with a battery, but also, of course, integrating what are the on-site renewable energy production. So this was the main point for in introducing and discussing this important of the overall flexibility and the awareness of the energy system, and why is pivotal the role of the energy management system that supervise and enable the energy experts of the energy intensive industry to be able to participate into flexible markets. So concluding this, the BESS introduced the storage flexibility. The high temperature heat pump introduced sector coupling flexibility, and also the valorization of waste heat. The improved available flexibility is thanks to the accurate monitoring and forecasting. So the capability and the possibility to solve the optimization problem, to know what is the optimal schedule of my generation assets, and in case eventually to participate into the flexibility market. And also some actions that are last two actions that are really important on also on decarbonization, direct decarbonization or inside decarbonization, are the efforts of decarbonization shared between companies, because the local district heating will benefit from a clean heat that is recovered by some farm, and increasing their decarbonization, supporting their decarbonization. And finally, the reduced environmental impact thanks to water savings, to what will be to the saved water not used for cooling, said before, thanks to the heat pump, the high temperature heat pump integration. Okay, we have space for questions and answer if you have any.
Thank you, Francesco, for your presentation. I don't see any questions at the moment, so maybe let's just wait another minute. But in the meantime, I just wanted to thank you again for your interesting presentation, and to remind everyone that the webinar is being recorded, so you can find the recording soon on our project website and on YouTube. So yeah, I don't see any questions right now, so I think we can close the webinar. Thank you so much, everyone, to having attended this meeting, and we will see you soon with the next Flex Industries project webinar. Thank you again.
Okay, thank you, Martina.
Thank you.
Bye, everybody,
Bye.
and thank you so much.
Bye.